Hello, I'm Alan Fulton, Irrigation and Water Resources Advisor in the Northern Sacramento Valley with the University of California Cooperative Extension. I work in the counties of Tehama, Glenn, Colusa, and Shasta counties. Welcome to this tutorial, continuing on with the discussion of how to use our weekly crop ET reports. I'm picking up on the subject of how it relates to soils and the use of a water budget. In this tutorial, we will review the steps and concepts to perform a field-scale water budget. After working through the steps, we will do some practice budgeting, so you can consider this management tool for your farm. So to perform a water budget and relate it to the soils that we are growing our orchard crops on, we must first assess the water holding capacity of our orchard soils. This depends on the site-specific characteristics. Here are three somewhat contrasting orchard soils that are common in our area. On the left is a Tehama silt loam. This is a relatively deep, uniform soil, high in silt content with minimal layering. And the soil profile is relatively uniform down to usually at least 4 or 5 feet, possibly deeper. The middle profile is an example of an arbuckle gravelly clay loam in this instance. The arbuckle gravelly clay loam is first characterized by being layered, typically higher in clay content in the first foot. Oftentimes there's a bit of a clay pan at the bottom of that foot where the clay accumulates over time. Then the soil decreases in clay content, increasing in sand and silt. And then as we move deeper, it actually can pick up back into off and on layers of clay and sand. Towards the deeper depth, we will find some evidence of gravel. This is a Kimball series. This series tends to have more gravel in the surface, sand and gravel in the surface, than the other two series. And as we go deeper, it gets sandier, and then the gravel becomes much more abundant in the subsoils. So these are just three examples that show that our orchard soils can have a wide range of conditions. Now, I'd like to review some basic phases of soil moisture conditions. On the left is a representation of a saturated soil. With saturated soil, all of the pore space is filled with water, and about 50% of this pore space will eventually drain its water due to the gravitational forces. Once it drains, we will reach a condition called fill capacity. At fill capacity, this is still a very moist soil that will hold a firm ball, or in a case of having enough clay and silt, it will form a ribbon as you pinch it through between your index finger and your thumb. At fill capacity, this is the highest combination of soil moisture and oxygen in the soil. At this point, most of the water that will drain by gravity has already drained. The third phase is the other extreme, and that is wilting point. At wilting point, most of the soil porosity is filled with air, and the only water on the soil is adhered so tightly to the soil particles that it's very difficult and not really available for our crops to get. So we have three phases in our soil moisture: the saturated, then we have the unsaturated that consists of a range from fill capacity to wilting point. To carry this out just a little bit further, we have our saturated soil, sometimes called gravitational water. When it's saturated, no oxygen. And this is a form of harmful crop stress too. Oftentimes we think of crop stress being caused by too dry of soils, but saturated soils depleted of oxygen can actually lead to more acute injury to the trees and death by cutting off the oxygen to the roots. As we mentioned earlier, we have fill capacity. This occurs when the gravitational water is depleted and drained away from the soil. We enter fill capacity. We move towards wilting point. As we go from fill capacity to wilting point, as the soil moisture changes and a crop's growing, it will go through a range of stress, from no stress to low crop mild stress to mild moderate, and work its way to higher, more severe stress. And we get to the wilting, and also called hygroscopic water, that water that's on the soil but cannot be extracted by the plant. And at this point, we're looking at severe crop stress that can also lead to death of the crop or the tree. Okay, so within the plant available range, from fill capacity to wilting point, depending on the soil textures and structure, or in the instance of a fine sandy loam, the water holding capacity in 1 foot of soil depth will range from about 0.8 to 1.5 inches of water per foot soil. Now, there is one concept that in the management of our soil moisture that we consider is we know that the crop's going to go through a range of stresses as the soil dries. And so we tend to set a management threshold of how dry are we going to let the soil get, and how does that correspond with what level of crop stress will incur. Usually for management purposes, it's quite common to set a 50% management threshold on your depletion of your plant available water. As the soil increases in silt and clay content and lessens in sand content, the water holding capacity goes up. Loamy soils and silt loam soils may have 1.5 to 2 inches of water per foot soil. So in one way, you can think of it as a bigger bucket of water that's available to hold the crop between irrigations. Soil is very high in silt and clay, and increasing in clay in excess of 30–35% clay content will hold even more water, 2 to 2.4 inches of water per foot soil. So you could think of it as even a larger bucket of water. And when you consider the management threshold, you will have a larger reservoir of water for which the tree can thrive on in between irrigations. So you can work with those general guidelines that I gave you in the previous slide, or you can use our soil survey information that is available to us online. We have 2 sources of soil survey information that are available. There is the NRCS soil survey web, and there is the California Soil Resources soil web. Here I show you the link for the Cal Soil Resources, and we're going to demonstrate the information that's in it and how we can use it to help us define our conditions so that we can run a water budget for our orchards. So you can use this website. It is Google Earth integrated. Here is a map of about 1,000 acres of farmland showing the soil contours. That's what these yellow lines are. And these abbreviations represent different soil mapping units that occur across this farmland. It does point out the level of variability that we deal with and are trying to manage. When you're in the website, you can click anywhere within these contour lines and bring up information about the soil profile. Here is an example. I click on the area that consists of the Tehama silt loam. It gives you a description of the depth of the soil profile, the A horizon and the B horizon. The A horizon is the horizon that has been most influenced by organic matter, plant material in previous farming activities. And the B horizon is deeper and less influenced by those factors. You can click on that link to the Tehama silt loam and drill deeper into the database. And here you will find a line that gives you information about the available water storage for that map unit. Now this is the available water storage. This is the difference between fill capacity and wilting point. And it tells us that there is 17.7 centimeters, this is in metric, water per 100 centimeters of soil. So to make the conversion from metric to English, I've done this over here for you. 17.7 centimeters of water divided by 2.54 centimeters per inch equates to 7 inches of water. That 100 centimeter profile divided by 30 centimeters per foot equates to 3.3 feet soil. So when I combine these two conversions, 7 inches of water divided by 3.3 feet, I get an estimate of 2.1 inches of available water per foot for this Tehama silt loam. That is the amount of water between fill capacity and wilting point for this particular map unit. We'll do a contrasting unit, the Arbuckle Gravelly Loam. Here you can see again the profile description tells you the depth of the A horizon. The B horizon gives you some information about the structure of the soil at those depths. You can click on this link here and go in deeper into the database. Here you'll find for the Arbuckle series, again, the available water storage and here it's indicating 13.6 centimeters. Making the conversion, 13.6 divided by 2.54 suggests 5.3 inches of plant available water, the difference between fill capacity and wilting point in that 100 centimeter profile. So converting 30 centimeters per foot equates to 3.3 foot of soil. 5.4 inches of water divided by 3.3 feet soil equals 1.6 inches of water per foot of soil for this Arbuckle series. So this is how you can use your online soil survey map information to help you begin to define the water holding capacities of your orchard soils for purposes of running a water budget for your orchard. The second piece of the equation is you're not done by just knowing the water holding capacity of the soil. We have to make some judgment call on what is the effective root zone. How many feet of that soil do we apply that water holding capacity number 2? There are a lot of observations and opinions about the effective root zones of perennial tree crops like walnut, almond, prune, and others. There's a lot less quantifiable data. We know it's certainly deeper than can be evaluated quickly with a shovel. In my years of monitoring with soil moisture devices, usually between 5 and 10 feet deep, I see a lot of evidence that we should be using at least a 4-foot root zone and probably more for trees that are 3 years old or older. One UCANR publication, 8571, titled Irrigation Management in a Nutshell, written by Daniele Zaccaria, Irrigation Extension Specialist in UC Cooperative Extension, suggests that for perennial tree crops, the effective root zone may be on the order of 8 feet. In some field trials and in some of my own monitoring, we have definitely observed soil water extraction in almond as deep as 7 feet, and in some cases in walnut as deep as 10 feet or more. Our next step that we need to do here is combine our knowledge of the water holding capacity for the orchard soil series that we identified using the soil survey maps and combine it with some judgment call on the depth of root zone. So here's an example. We'll call this orchard A1. I'm going to define my plant available water by putting a limit on it, saying I'm going to define it for a 50% management threshold. In other words, I want to know how much water within the root zone I have, yet the soil will not be depleted more than 50% of its total plant available water. So in this example, the soil series is the Tehama silt loam. I walked you through and showed you the calculation that a reasonable number would be 2.1 inches of water per foot soil. In this instance, I'm going to use the number that I have evidence of an effective root zone that extracts water at least 7 feet deep. So I'm going to use a effective root zone depth of 7 feet. So the calculation is this: 7 foot root zone times 2.1 inches per foot equals 14.7 inches total plant available water. Now, you may find that the profile doesn't extend uniformly 7 feet deep and need to make some adjustments on this number. But for today's discussion, this is what we're going to work with. The next step is, if I have 14.7 inches of total plant available water from fill capacity to wilting point for a soil profile of 7 feet, but I want to put a management threshold on it of 50%, that I want to try to manage to keep it at that level or higher, my plant available water would then be 14.7 times 0.5 or 7.4 inches. Okay, let's change the conditions a little bit with a second example to estimate the plant available water. This is orchard A2. It's almonds. It is the Arbuckle Gravelly Loam series. The water holding capacity for each foot is not as high, 1.6 inches, nor do we expect the effective root zone to be as deep, 4 feet. So the math is like this: 4 foot root zone, 1.6 inches per foot of available water holding capacity for a total of 6.4 inches total plant available water. I'm going to continue to apply the 50% management depletion threshold. So 50% of 6.4 is 3.2 inches of plant available water under this scenario. So I walked you through the process of assessing the plant available water for specific orchard conditions, using the soil survey information and using your judgment and knowledge of what you think the effective root zone is. Also sharing some of my experiences with you. With this, we need to ask the question, will the orchard root zone be refilled at the start of each new season in the spring? This is a good question and one that's, the answer is not always the same. But for those of us growing deep-rooted perennial crops in the Sacramento Valley, our rainfall is generally between 15 to 20 inches a year on average. If 50% of that is effective, we should be able to store at least 10 inches, 7.5 to 10 inches of rainfall in our soil profile. Now, on drought years, of course, there will be exceptions. But what this is suggesting to us is that in many years, and it's been my observation in about 20 years that I've been working here, I've experienced maybe 2 years that did not have enough rainfall to re-wet the soil profile at least 5 feet deep. Okay, so but for most years in the Sacramento Valley, it's a pretty good bet that we're going to have a good deep profile. As you move south in the Central Valley, it's a different story. As you move into the drier climates, and definitely in the far south of the San Joaquin Valley, it's unlikely that you're going to start the season with a very deep soil moisture profile. Okay, so one sure way of knowing whether you're starting each season with a full profile of moisture is to check it, okay? So one technique is using a fill method, going out with an auger or a post hole digger, digging at least 3-4 feet. I would prefer 5 or 6 feet, and handling the soil on the way down. Doing this probably in the month of late January, mid-February, so you have some idea what's going on in the event that you're really short on moisture and you might want to consider some winter irrigation to replace what the rain has not brought. Okay, so here's a little bit of just a reminder of the idea of handling soils to evaluate their water holding status. Sandier soils when they're wet, should make a firm ball. It should definitely leave a film of water on your hand. Silt soils will make a very clear, firm ball, leaving moisture on your hands and possibly begin to ribbon. And clay soils that are wet will leave a lot of moisture on your hand, but they will also ribbon 1-2 inches out or more by pinching them between your thumb and your index finger. When the soils are dry and can still hold a lot more water, they're going to be crumbly. They're not going to leave as much moisture, evidence of moisture on your hand. In the case of clays, they will maintain their aggregates and they'll be small clods. So these are the kinds of things that you can look for. I like to refer people to a very nice publication. It's called Estimating Soil Moisture. It's published by the NRCS of the USDA. You can find it by simply Googling USDA Estimating Soil Moisture. It's a nice publication with pictures to help you develop your skills at evaluating soil moisture by feel. If you're looking for a soil auger or a probe, here are some suggestions. I don't intend to be endorsing anybody. These are just some that I am aware of and have used in the past. JMC soil samplers, AMS samplers, and forestry suppliers. Another very good way is to invest in soil moisture sensors to help you follow the extraction processes through the growing season and the refill during the off season. Okay, we're down to about 2 slides left in this tutorial. And what I'm going to try to do here is I want to bring together the information about the soil water holding capacity and the information that we send out to you each week with our weekly crop ET reports. And in this instance, consider the question, when should I apply that first irrigation? I have purposely selected out almonds for the 2020 season. This is the ET report dating back to April 10th through April 16th. Leaf out April 1st. So we'll take a look and apply this information here. With the question in mind, when might I apply the first irrigation? So we will look to that orchard A2, which was the Arbuckle series. More shallow 4-foot root zone, 1.6 inches of plant available water per foot soil, totaling 6.4 inches of plant available water, assuming we got enough rainfall, which was the case. Applying the 50% management depletion threshold, that limits my plant available water that I will allow to be depleted to 3.2 inches in this situation. So here's the thought process, 3.2 inches of plant available water to start with as the trees leaf out and to hold me over until I begin to think about irrigation. From March 1st to April 16th, our crop ET records show a cumulative ET of 3.9 inches. So we've exceeded the 3.2, the plant available water. However, our report also shows in that same time frame, we received almost 2.7 inches of rainfall. Now, because of my experiences, I credit only 1/2 of the rainfall as effective. When I have allowed full credit to the 100% of rainfall, when I've studied these water budgets, I've observed they tend to fall behind. So this is just something I've learned from experience, and it's a judgment call on my part. So I've got 2.6 inches of cumulative rainfall offsetting the 3.9 inches of crop ET for the same period. The math and the thought process is this: 3.2 inches, I started the season with 3.2 inches of available water in the soil. Time has lapsed from March 1st through April 16th, about 45 days, and that represents 3.9 inches of ET. During that same period, I have credited back 1.3 inches in effective rainfall towards the crop ET. So 3.2 minus the 3.9. So we got the credit for the storage. We've got the debit for the ET. We've got the credit for the rain. We have a net balance of, we are still 0.6 of an inch above or away from the 50% depletion mark. So when I consider the question, might I wait another week or begin irrigating? First, to keep this in perspective, this is an estimate. And so What I know is that it's getting close. And if I choose to begin irrigating because of what I've sized up now, or if I choose to wait a week, will probably be driven for me by what is most concerning to me about my particular orchard. Do I have any history of tree loss? Have I been concerned with diseases, root diseases? If I have, I might delay a week. If I'm feeling pretty good about things, I might go ahead and pull the trigger and start the irrigation season. The next question is, well, how much water would I apply? We're working with micro sprinkler and drip systems, okay? Just because we're showing a 2.6 inch depletion, or we're 0.6 of an inch shy of 3.2, which makes it 2.6 inch soil moisture depletion, it does not mean I have to run the system long enough to put all that water back. Most of our micro sprinkler systems and drip systems apply water somewhere between 300ths and 600ths of an inch per acre. I would probably settle for a typical 24-hour set or so and put 1 to 1.5 inches of water back on, and consider that I'm now just on course to begin getting into the irrigation rotation. By doing this, I'm guarding, I'm not trying to put all the water back and not risking overly saturating the soils and providing an environment that's conducive to root health problems, low oxygen and disease. Yet at the same time, I am now in the cycle to irrigate and start to try to maintain my soil moisture at reasonable levels. From this point forward, it may be a case of getting the weekly ET report and approximately putting back on what's used. I can keep in the back of my mind this 3.2 inches of representing a 50% depletion, and kind of keep that in the back of my mind and see if I'm maintaining a long-term balance over the course of the season. Okay, last slide. I'm going to just kind of change up the scenario a little bit to help practice using the water budget to make decisions. Same soil, the Arbuckle series, the same 3.2 inches of plant available water at the 50% management threshold. But now I'm going to change up the weather conditions and how that affects the crop water demand. I'm going to use the Colusa County data for almond. Here it's the cumulative ET for the same time frame from March 1st to April 16th is slightly higher than in Tehama County, 4.35 versus 3.9. What's most noticeable is that the rainfall is in that same period has been substantially less than in Tehama County. We have I'm really only crediting in this water budget roughly a 1/4 inch, 0.52 inches of rain at 50% effectiveness, so 0.26 or a 1/4 inch of rainfall towards supplying this 4.35 inches of ET. So when I think this through, I had 3.2 inches of stored water. From leaf out till 16th of April, cumulative estimate of 4.4 inches of rainfall, of ET, crop ET. And I had a small credit of a 1/4 inch of effective rainfall. So I add the numbers. 3.2 is what was in storage, minus 4.4 is the debit against it. 0.3 credit for a little bit of rainfall. I find myself running 0.9 inches less beyond the 50% depletion level. So what this is telling me is if I haven't already began irrigating, I may certainly want to consider it, unless I have other information that tells me otherwise. It'll be a subject for another time, but if you're using a pressure chamber, it may not always agree, okay? But at least this water budget puts in context what's happening below ground with the soil, with the water balance. And if I haven't began irrigating yet, I probably would seriously consider it. I'll reemphasize, just because I've dried down and my deficit is estimated to be on the order of 4.1 inches or 9/10 of an inch beyond 3.2, it does not mean that I need to put all that water back on. What it's really telling me is I just need to get going with my irrigation routine and start trying to stabilize the situation. Okay, so I would be comfortable with trying to get 1.5 to 2.5 inches of that water back. That would get me on track to stabilize things. It would also help me guard against overly saturating those soils and creating tree health problems. Okay, this was a fairly long tutorial. I hope it demonstrated to you, though, how to make the connection between our weekly crop ET reports and the soil water holding capacities of our orchards, and showed you a little bit what's involved in the thought process of using a water budget to manage water in your orchards. Thank you.